So let's define some different types of molecular orbitals. We have two categories, bonding molecular orbitals and anti-bonding molecular orbitals. And within each of those categories, we have both sigma and pi type of interactions. So the sigma interaction occurs when we have orbital density along the bonding axis. So, of course, the orbital density means electron density, ends up being there too. But between the two nuclei, so the bonding axis, or I'm going to call it the internuclear axis. It means the same thing as the bonding axis, but it's just saying the axis between the two nuclei. Pi bonding molecular orbitals, by contrast, are going to have the orbital density above and below the bonding axis. So we already actually saw this in our discussion of the localized electron model. So that is still true here, that when we have pi interactions, the orbital density lies above and below the internuclear axis or the bonding axis. That means that in a pi bonding molecular orbital, you actually have a nodal plane, so a region of 0 electron density. That nodal plane incorporates both nuclei. And I'm going to draw this in a second. After getting these definitions down, I'm going to draw this. So that both nuclei are kind of in this region of 0 electron density. And for the pi bonding molecular orbital, you have the actual orbital density above and below the internuclear axis. Okay, so that's the difference between sigma and pi. Now, the same goes for anti-bonding molecular orbitals. Of course, those we denote with a star, so sigma star and pi star would both be anti-bonding molecular orbitals. And here, the same thing is the case. The orbital density is along the internuclear axis. So it's the same situation, except that you have a node that is perpendicular to that internuclear axis. All right, I will draw that in just a moment. For pi star, once again, you have the orbital density above and below that axis. Okay, what does this look like? So for both of these, for both the sigma star and the pi star anti-bonding molecular orbitals, there is a nodal plane. So the nodal plane, once again, is a region of 0 electron density perpendicular to the internuclear axis between the nuclei. All right, maybe that will make more sense when I make some drawings. So I want to draw an example of each of these types of MOs. The bonding and the anti-bonding, sigma and pi. So I'm going to make a little table here to organize my drawing. I'm going to have sigma and pi. And of course, the anti-bonding will be sigma star and pi star. So the sigma bonding molecular orbital just looks like a region of enhanced electron density between the two nuclei. The pi bonding molecular orbital has a nodal plane between the two nuclei, and then it's going to have regions of enhanced electron density above and below those nuclei. Okay, so here there's a nodal plane that incorporates the nuclei. So for forming a pi bond, you have the interaction above and below the bonding axis, and those two lobes have opposite phase. For the anti-bonding sigma molecular orbital, we've kind of already seen it for hydrogen, we have these oppositely phased regions. I'm going to give them different shading to show the opposite phase. And then in between them, you have a nodal plane. So that nodal plane is perpendicular to the internuclear axis, as you can see. For the pi star molecular orbital, that is going to look like, well, here, we're going to draw the two nuclei of the bonded atoms. And then what you have is this destructive interference where you have oppositely phased lobes above and below the bonding axis. And if you look here, you have two nodal planes. You have one nodal plane that incorporates the nuclei. Let me erase that. So, and then one nodal plane that kind of is perpendicular to that internuclear axis. So let me kind of draw those here. So two nodal planes exist for the pi star antibonding molecular orbital. So that's a very destabilizing interaction, as you can imagine. One of the nodal planes incorporates those two nuclei, and one of the nodal planes divides those two nuclei.